So we already saw about the 7 stages in NLP pipeline. So the 7 stages we saw about the data gathering. So we saw about the text pre-processing methods, and we in this text pre-processing we saw the different methods like tokenization, stemming, lemmatization, stopword removal, and those kind of techniques. So after all these steps are over in the NLP pipeline, next we move into the text representation. So in the case of text representation, what this text representation, some people used to call this text representation as a feature representation. So it's like interchangeable terms. So we'll try to go with the text representation. So text representation is going to convert your raw text. So whatever the text you pre-processed, so that particular text into the machine readable format. So as we say machine readable format, so machine readable format is mostly a number kind of things or a vector kind of things, because machines can understand only the numbers, doesn't understand the text, right? So we need some methods or some algorithms or some techniques which is helpful in converting your raw text into the features or raw text into the representation. So that is why we will be looking some of the methods in the NLP pipeline for the text representation. So as we all know that humans are good at like a text, but the machines are good at number. So we need some techniques which is going to bridge the gap. So that is what we are going to see in the text representation. This is a crucial step because we need to select the correct text representation techniques based on the problem which we're trying to solve, because due to some improper kind of techniques your model performance will be get affected. So we'll see how the methods are working and what are the limitations and what are the advantages of each and every method over another method. So in the first technique we'll be seeing a one-not encoding. Okay, so one-not encoding basically is going to assign a 0 to all the elements in a vector, except uh, okay, so we will use the notebook here. So let me write something. One second. Okay, so we'll see one-not encoding. So in the one-not encoding, let us say I am going to represent a text. What the text is, let us say the text is going to be I love NLP. So this is the text, okay? So I'm going to represent the text in a form of number. So what technique I'm going to use? I'm going to use the technique called one-not encoding. Okay, so fine, so perfect. So how am I going to do? So first, let us consider the vocabulary for the text. So vocabulary is a set of unique words which you're going to have in the text or a corpus. Corpus is nothing but a group of documents. So in this case, you have only one text. So your vocabulary is going to be something like this. I, love, NLP. So this is what your vocabulary. So you can write your vocabulary like this. So I use a different color for the vocabulary. I use red for vocabulary. I love NLP. And this is we call it as a text one. So this text one can be represented as this is going to be I is going to represent as one. This is going to be I. So this is going to be 0, 0. And for the term love, it's going to be 0, 1, 0. And for the term NLP, it's going to be 001. So the text which is I love NLP can be represented as so this is what we call as a one-not encoding. Okay, for example, let us say we have a different terms. Okay, so let us say we are going to have a different terms. Let us say I have a two text or two documents in my corpus. Corpus is a collection of different type of documents or different type of text or different type of records. So let us say I'm going to have two different texts. So the text one is going to be I love NLP, and the text two is going to be I love teaching. So these are the two texts, these are two texts which is present in my corpus. Now we will be finding out the vocabulary. So now we will be finding out the vocabulary. Vocabulary is a set of unique words, right? So from the two texts from the corpus, we can say the unique word is going to be I, love, NLP, teaching. So these are the unique words present in your vocabulary. So for example, your text one, that is let us take one by one. For the text one, that is I love NLP, which is going to be your eyes can be represented as 1, 0, 0, 0, and your love is going to represent as 0, 1, 0, 0, and NLP is going to represent as 0, 0, 1, 0. So all together, put all together, you're going to represent your text one as 1, 0, 0, 0. This is for the word I, and this is for the word love. This is for the word NLP. So put these all together, we'll get the text representation for the text one. Okay, fine. Now I need to get the representation for the text two. How am I going to do? So using the same vocabulary, I'm going to build a representation for the letter I. Is going to be 1, 0, 0, 0. How would this 1, 0, 0? You see the vocabulary. The letter which we are trying to use is like I. So you see where our I is present. In this particular case, you put the binary value of 1 for the particular value, and remaining all the value you put it as a 0. So next you have the term love. So if you take the term love, it's going to be 0, 1, 0, comma 0. And if you take a teaching, so teaching is going to represent as 0 because I is there and love is not there and NLP is not there and teaching is there. So you put 1 over here. So this is teaching. So put all this together. So you get the text to root 2 representation as 1, comma 0, comma 0, comma 0, 0 comma 1 comma 0 comma 0 and 0 comma 0 comma 1 0 comma 1. So this is the way of representing your text as a one not encoding. This is the more a primitive kind of thing, so it's a, like a trivial one. So it's like a, people have been started using the representation starting from a one not encoding in the beginning. So nowadays no one is using a one not encoding because it's a kind of trivial one. So this one not encoding will be having some amount of some kind of disadvantages. Let us see what this disadvantages is actually. So from that you can see that this are going to assign a 0 to all the element in vectors except for the one which has a value as 1. This value 1 is going to represent from the vocabulary. So let us say I'm going to have a sentence, I love my dog. So each word is going to represent like this. For example, first you need to create a set of vocabulary. You need to create a vocabulary. Vocabulary is a set of unique words. So you just say, you put a vocabulary, and from the vocabulary you do the one not encoding and you have a representation like this. Put all this together, you will be getting 1 comma 0 comma 0 and comma 0 comma 1 comma 1 comma 0 and 0 comma 0 comma 1 comma 0 comma 0 comma 0 comma 0 comma 1. So this is what the one not encoding is going to work in from the beginning. Next, let us say we see some advantages and disadvantages. Advantages is like kind of easy to understand, right? So it's very trivial kind of thing, so it's easy to understand. So next one is like a disadvantage. What is a disadvantage? This is computationally expensive. Yeah, it is computationally expensive because let us say you're going to have a millions of words in your corpus, because nowadays you'll be having a millions of records, right? So if you have a millions and trillions or a huge amount of records, it's computationally expensive. And there is some problem which is going to happen, that is it doesn't care about a semantic information. So semantic information in the sense it doesn't capture about any real meaning of the word or real meaning of the text in the corpus. So that is one of the disadvantages for the one not encoding. So next one is something called as out of vocabulary problem. Okay, so what is out of word vocabulary problem? So in order to tell what is out of word vocabulary problem, let us go back to the notebook. So let us say I train my model because okay, fine. So if you are building any machine learning model, so you basically divide your model into two teams. You will be training your model with the help of training set. So what is training set? Let me explain 1 second. So another one is your testing set or testing data. Let us say I have a model. Okay, so I'm going to build a model. I have a records, as we already see, right? So we have a records like spam classification. That is my task. So for the spam classification, let us say I have 1,000 records or 1,000 rows. Rows means records, like a number of rows you're going to have. That is a record, right? So I have 1,000 records. So in the 1,000 records, I am going to take 700 records for training and 300 records for testing purposes, because we need to evaluate the model. To evaluate the model, we go for the train testing records. So this is I will explain in detail in tomorrow session. For sake of simplicity, let us assume that you are going to use a 700 records for training. So in the 700 records for training, you will build the vocabulary if you are using a one not encoding only for the 700 records. Okay, so and you build one vocabulary. That vocabulary size is extremely large. Okay, fine, never mind. So let us say that vocabulary is going to consider of an NLP, free, hello, hi, and different kind of text. Okay, it's perfectly fine to train the model with the 700 records. Let us say we are going to test it out with the 300 records, right? So if suppose if any one of the records, let us say that the text is going to be hey, are you free, can we meet at SNH Chennai? Okay, fine. So in the 700 training records, we'll be creating one vocabulary, right? So that vocabulary contain all these words except this SNHNI, right? So where do you represent SNHNI? Because you will be representing as every features with the help of your vocabulary mapping, right? So in my vocabulary, there is no word called SNHNI. How am I going to handle those kind of things? So that kind of problem, which we called as an out of vocabulary problem. For example, whatever training record I'm used for the training, with the help of that particular training record, I'm going to build the vocabulary. So there are some words which may not present in the vocabulary, which can come in the real time, right? So how am I going to handle those kind of words? That is called as an out of word vocabulary problem. So perfectly fine. So this is what the problem which we're going to talk about, out of word vocabulary. So this problem we cannot able to handle by using a one not encoding. So these are some kind of disadvantages. So I'm repeating again. So this one not encoding is a kind of like a basic form. So we are going to for every corpus is a set of documents. So from the set of documents, you are going to create a vocabulary. Vocabulary is nothing but it's going to have a set of unique words, and from the set of unique words, you are going to represent the features? How am I going to represent the features? I'm going to assign the value to 0 to all the elements except for the one which is present in the vocabulary right now, and I'm going to put the value of 1. So this is what the one-not encoding, and we saw the advantages as well as the disadvantages. Now we will be moving into the second technique. So what the second technique is actually, so second technique we call it as a bag of words. Okay. So what is meant by a bag of words? So we are going to deal with a bag of words, right? So bag of words is nothing but, let us say, right now what we are doing is we are going to put simply one to the place where that particular text is occurring, and the index is going to be the place where we put in a vocabulary, right? But we doesn't care about any frequency of words. So frequency of words in the sense, let us say I love NLP, and another sentence going to consider I love teaching. So I didn't care about the frequency of the word. For example, I occurs 2 times, but I put only one in the representation. I didn't care about the frequency of the words. So this bag of words is a technique which is introduced in order to gather, in order to focus, or in order to give more attention for a frequency of words. Because in this particular case, there is some words need to be occur frequently to represent some kind of documents, right? So your frequency of words matters a lot. So people have started thinking of the next method. So next method they came up with something called bag of words. In bag of words, what we are trying to do is each word in the text, right, is considered as a feature, and we are going to calculate how many times a particular word is going to occur, and we are going to represent those kind of things. For example, if you take the corpus, okay. So what is corpus? As I just said, corpus is nothing but it is a set of documents, documents, right? So let us say first one is considered of the cat in the hat, and another one is like the dog in the house, and another one is the bird in the sky. Okay. So now perfectly fine. So if I create a vocabulary for these three words, my vocabulary is going to be dog, cat, bird, in, house, sky, the hat. Okay. Perfect. So these are the vocabulary which I can generate from these kind of corpus or the documents, set of documents. Perfectly fine. Now what I will be doing in case of one not encoding is I just see, okay, the first word is the, right? So I'm going to see where are the occur, and I'm going to map those kind of things, and I will put. I never care about the frequency of words. Okay. So in this case, for example, if you see the first text or first document, you see the cat in the hat. So my vocabulary is going to be kind of these things. So I will search for the. Where is my the is located in my vocabulary? It's located at the last before index. So I'm going to count how many number of times the word occurs. So in the text, let us say in this case, the occurs 2 times. The cat in the hat. So it occurs 2 times. I'm going to represent the value as 2. Next one is a cat. So if you see for the cat in the vocabulary and you see it's in the first index or second position. So the cat is going to be 1 because in the whole text, the cat appears only 1 time. So I'm going to put it as 1. Next, I will be looking for the word in. So in my vocabulary, where is my in is present? My in is present in the fourth position. So I'm going to count the number of in my text. So it is only 1. So I'm going to put 1. And then there is already represented over here. So then we are going to have a hat. What is hat? So I look for my vocabulary. Okay, hat is present in the last position. I'm going to put the number of times the hat occurs in the text one. So in this case, the hat occurs only 1. So I'm going to put it as 1. Okay. Perfect. So this is for the text one. So now we move to the next text or the next document. So we see the dog in the house. So now you look for the word the. So in the vocabulary, it's present 1 before the last word. So now count number of times that the occurs. So we are basically calculating the frequency of each and every word in the text, and we are representing in the vocabulary context, or we are representing in the feature representation. So that is what we will be doing in the bag of words. So in this case, the will occur 2 times and everything will be a similar one. Or the last one is also the will occur 2 times. So this is what we are trying to deal in the bag of words. So now the bag of words, as compared to the previous methods, what it's trying to do is this bag of words is able to something like from the previous method is going to say, okay, I'm going to consider the frequency of words. That is considered to be some of the added advantage. Rather than putting a simply ones and zero, I will be putting something in a number scale because the scale is going to represent the frequency of words. Okay, perfectly fine. So these techniques are like improvement of a one-not encoding. So this is going to works only based on the number of frequency or number of words or number of frequency in the documents which we are trying to deal it. So this particular thing is going to ignore your grammar perfectly because it doesn't capture any word order, any semantic information. It's just going to count the word and going to represent. It doesn't keep track of the order in which we are doing. For example, let us say I'm giving a sentence like the cat in the hat. Okay, so the cat in the hat is something says that the cat. So for example, let us say the dog in the house. Okay, so to be more clear, the sentence or the meaning conveys that there is a dog which is present in the house, the dog in the house. But for example, let us say you rearrange the term, the house in the dog. It doesn't make any sense, right? The house in the dog. So let us see, you're going to get the same text representation. So it ignores the grammatical meaning. It ignores the grammatical meaning. It doesn't make sense of any grammar. It doesn't give importance to the grammar. It's just going to consider the frequency of words. So that is one of the key important problem which we're going to face on the bag of words. And as I said, there is no grammatical practices, and it only keep track of frequency of words. It doesn't give the importance other than frequency of the word. So these are the considered to be the disadvantages kind of things. So another disadvantages which we are going to see in the method is it going to give an importance to the word which are occurring more, right? That is what we see in the basic definition. For example, let us say there is some person who doesn't remove the stop words. Okay, in the pre-processing step, there are some stop words like there are many stop words, right? The stopwatch are the word which is going to occur more frequent, right? In this case, for example, if you forget to remove the stopwatch, he is going to give more importance for the stopwatch only. So at that particular case, your machine learning model will forget to learn about the any new important keyword. For example, let us say there's something called COVID. COVID exists only in the year of 2019, 20, and 21. Before 2019, the word COVID doesn't exist. But there is say something someone is going to predict, oh, COVID is going to come. At this particular time, there is no word called COVID in your vocabulary. So you are going to give a less amount of an importance to the word, but that is an important word, right? So importance of the word is captured only in terms of the frequency. So we are not capturing anything which is specific to the term. So we'll see how this another method is going to overcome of these limitations, and we'll see the advantages like a fixed kind of vectors. Yeah, it's obviously fixed kind of one based on the vocabulary. So we will try to see n-gram. So this n-gram is like what we're going to derive from the bag of words. Okay, so bag of words next derived version is in n-gram. So n-gram basically a representation techniques which is going to break your text into the continuous sequence of n-grams. Okay, let me explain what does this actually means. We will take a text. Okay, let me take a text as this is my text. I love NLP course. So let me take this text. Okay, so after taking this text, let us say unigram. Okay, what is meant by unigram? So unigram you also say as 1 gram. So in the unigram, what you're trying to do is you're going to break each and every single words together, each and every words, every single words. For example, this is going to be I love NLP course. And after dividing this individual tokens or individual grams, you will calculate the feature representation. So that is what you're that is that is what you're going to do it in case of an unigram analysis. Okay. Now in case of bigram, what we are trying to do is bigram is nothing but it's a 2 gram. So this is going to be something like this. So you'll take the words in a two-way manner. So the first two words will become as a single word, I love, and another word is going to be love NLP, and the last word is going to be NLP course, something like that. So you're going to break into the two words. So that is called as 2 gram or bigram analysis. And the third one is going to be trigram. In case of trigram, what we're trying to do is you're going to break the words into the three characters or three words or three tokens together. So in this case, it's going to be I love NLP course. So something like that. So you're going to carry forward the three words on breaking. So if you repeat up to n times or n values, it's going to be m-gram. So you can take up to your own choice. You can also have your feature representation, which is going to represent with your unigrams, bigrams as well as trigrams. So we will see how to implement these things in code like hands-on session. So which is going to happen after the theory class. So we'll see how this particular n-gram analysis is going to happen. Okay, perfect. So here the n-gram is basically breaking down the text into the sequence of n words, right? So n-gram is like a bigram or unigram where the value of n is going to be 1. In case of bigram, the value of n is going to be 2. We are going to break into the set of 2 consecutive words, and trigram is going to be a set of 3 consecutive words, and we have n-gram is a set of consecutive n words. Perfect. So, okay, fine. Let us take this example, the dog in the house. So if you take the sentence dog in the house, your unigram is going to be the breakage of one sequence or one tokens at the time. So it's going to be the dog in the house. So if you take a bigram, so bigram is a combination of two sequence. It's going to be the dog in the house. So in case of trigram, so trigram is going to be the dog in and the dog in is going to be a one word, and in the dog in the is going to be the next sentence of things, and in the house is going to be the next one or next tokens. So this is a trigram analysis. Okay, from this you can capture something because we are giving some importance to the sequence, right? So in the previous example, we care only the single words. So in the single words where we forgot to capture some semantic information, not only semantic information, we forgot to capture some the order of the words in which they are arranged, because we calculate only the frequency, or else we calculate whether the present is word is going to present. I'm going to put 1 or else 0. So that is what we consider in the past. But in this case, what we are trying to do, we are trying to do somewhat like the order of the words in which they are arranged. We are going to give an importance, because if you take a unigram or if you take a bigram or trigram, you say the dog. Okay, fine. The and the dog, and the dog and the okay, the and the house. So we get some more huge some more extra information as compared to the unigram. So if you see the dog and so you get huge amount of information. So we can able to capture semantic meaning up to some extent, not fully but up to some extent. So as we said, like yeah, the computationally expensive, yeah, it's a computationally complex. So it's like terrible, like if you get a millions of words, so it's computationally expensive. And again, oop problem doesn't handle, right? So there is some problem in which your normal traditional techniques lacks in case of out of word vocabulary. So this particular things will be only resolved if you go for the word embedding kind of things, where you'll be explored through some ANN neural networks. So neural network model is better in generating those kind of things. So there is a who problem is not handled again. So this is what we try to do in case of an n-gram analysis. So next method which you're going to do is something what wow kind of things. So because this is like even now that TF-IDF method is used in various application and various methods. So we'll see how this TF-IDF method is going to work. So TF-IDF. Okay, let me explain the abbreviation for the TF-IDF. So TF-IDF is nothing but it's a term frequency or inverse document frequency. Okay, what is term frequency and inverse document frequency? Okay, let me say, in case of bow is going to interrupt the importance of words in the document, because like the bow, there are some techniques which need to be improved, right? Bow, right? So that is what the people going to came for the TF-IDF. Okay, what's special in TF-IDF? So TF-IDF, like it's going to weight the words. It's going to give the importance to the each and every words on how often they occur in the document, like document in the sense how often they occurs in the same sentence, as well as how common they across all the documents. Let us say I have a document, I have a corpus. Corpus is a set of documents, right? I have a data set. A data set can be mapped as a corpus to a certain extent. So let us say I have a data set. So in the data set, each and every rows I will be considered as a document, and data set I consider as a corpus. Okay, perfect. So I'm going to measure how often a word is going to appear in a document. That means how often each and every word is going to occur in the same row or same sentence, versus how common they across all the documents, versus how common each and every words in the record of the data is going to occur along the data set. Let us say I have a data set. Okay, so you can imagine up to a certain extent, like we say okay, so corpus. Corpus is a set of documents, right? So in this case, you imagine corpus as a data set, like a spam data set or something like that, and documents. Okay, so you consider documents as a records or rows. Okay, so let us say I have a data set like this. It's going to consider category spam, ham, and something like that, right? So I have a messages over here, I have messages over here, I have messages over here. So this all together is called as corpus. Each and every record or rows, which we are going to call it as a documents, right? So these are some terms which is easy to for you to understand. So that is why I wrote a diagrammatic representation. Now we'll see. So the term frequency inverse document frequency method is going to work in a such a way or such a fashion that it's going to compare how often your word, okay, each and every word, or maybe a bigram or trigram, how often a word is occurring in the documents. That means how often a word is going to occur in the message of the particular row. And also not only those kind of things, and also how how the word is occurs in each and every documents. So how the following word x is going to occur on the different documents, like different rows in the data set. So that is what we are going to measure, and we're going to give some score. So that score is going to lies between zeros and one, 0 to 1, between 0 to 1, and we calculate the importance to each and every word. So that is what we're going to calculate in terms of TF-IDF. So I hope this will clear. So let me explain what is term frequency and what is inverse document frequency. So moving ahead, so this is the formula. Okay, fine. Term frequency inverse document frequency is nothing but TF into IDF. You can imagine like TF into IDF. What is term frequency? We'll see in a couple of minutes. And what is IDF? IDF, there is a formula, right? So the formula to calculate your inverse document frequency is log times of total number of documents. That is total number of records which is present in a data set. That is called total number of documents divided by number of documents or the number of rows, okay, of containing the particular term. Let us say there is a data set which is a spam message classification. I am going to take a word called Muthu. So if I want to take a word called Muthu, I'm say, let us say IDF, inverse document frequency is going to be like log of total number of documents. Let us say my data set is going to contain 1000 values or 1000 records. So it's going to be log of 1000 divided by number of records that contain the term Muthu. Let us say there is a in the 1,000 records. Let us say in 10 records, like 10 records, there is a token or there is a word called Muthu occurs. So the denominator will become 10. So it's going to be log of 100 by 10. So log 10. So this is how we will be trying to calculate it in this document frequency. We will explain how to calculate with the example of a worked example. We will see how to calculate TF and IDF. Okay, coming back to term frequency. What is term frequency? So term frequency is nothing but the number of occurrence of the word is in the documents is divided by total number of terms in the documents. For example, if you take the text or if you take the document or if you take the record, you are attending NLP session. Okay, so this is a text which you're trying to see right now. If you take this following document or a text or a record, let us say we take the word NLP. Okay, so I'm interested in calculating the term frequency for the word NLP. So you see, okay, the formula for NLP is, so for the formula for that term frequency is number of occurrence of the word in the document. Okay, so how many times the NLP is occurs in the whole sentence is going to occur only one times, divided by total number of terms in the documents or total number of terms which is present in the text. In this case, the total number of text or the total number of words which is present in the text is 1, 2, 3, 4, and 5. So it's going to be 1 divided by 5. 1 divided by 5, 1 is nothing but the number of terms the word NLP occurs divided by total number of terms in the document. For example, if you took the word attending, so you can define the formula as number of times the word attending is occurs in the text divided by total number of terms or total number of words which is present in a document. So in this case, it's going to be 1 by 5 because only one times the word attending is occur in the whole text. Let us say an example. You are attending NLP session from the coding club SNUC NLP division. Let us take this example. So if you want to calculate the term frequency for the term NLP, it occurs 2 times. So it's going to be 2 divided by number of len of words. So you can say len of words, len of text. So to be more approximate, the len of text. So this is what we call as a term frequency. Okay, fine. So what is inverse document frequency? Okay, so the inverse document frequency is like the total number of documents in the corpus. So total number of documents in the corpus in the sense total number of records divided by total number of documents with the term T or the whatever you're trying to calculate the IDF. No, the term we called as a T. So that many times the number of term T is occurs in the each and every documents. So to be more clear, you see the same formula. So it's going to be total number of documents, total number of records divided by total number of term which is going to contain the term NLP, total number of records which is going to contain the term NLP. Okay, why we are doing this? What is the need for doing this? Okay, so there is a need. Okay, so if a word which comes in all documents, okay, so let us say there is a word which occurs in all the documents. So if your bag of words will be giving a more amount of importance, right? Because it's going to calculate only on the basis of a frequency. So but I don't need, because if all the words occurring in every document, I don't need to give huge amount of an importance, right? So I need to look for the word which is at least occurring in each and every document. For example, let us take a corpus which talks about the COVID virus. So before 2019, there is no COVID, right? So there is some document talking about the COVID virus, which is really relatively more important, right? I need to give the importance for the word which is occurring least in the documents. So that also I need to keep in my mind. Not only that, also need to keep the in my mind like a term frequency also. So they came up with something called term frequency in inverse document frequency. Okay, let us say you keep that importance of the two terms. One is a term frequency, and you keep your IDF. So what they're trying to do is you give more importance to the word which occur more amount of in a single document into the word which is commonly in the present in the corpus. So for example, this IDF is going to give the value relatively less if the word present in all the documents. For example, let us give you an example. We have a 3 document or 3 rows or 3 documents in a corpus. So in the 3 documents, let us say there is a word called NLP, which is going to occur in the every 3 doc in each all the 3 documents. So your inverse document frequency is going to be log of 3 by 3. Because why 3 by 3? So the numerator is going to be number of documents present in the corpus, that is 3 records. So divided by total number of times the word NLP is occurs in your corpus, that is every row will contain NLP. So it's become 3. So log of 3 by 3 is going to be 0. Okay. So now, for example, if you take a word called SNUC coding club, so the SNUC coding club only occurs one times in the document, like first documents among all the 3. So you're going to calculate the idea for the SNUC coding club is going to be 3 divided by 1. Because why 3 divided by 1? 3 is going to be the number of corpus divided by 1 is nothing but number of times the SNUC coding club is came under all the set of documents. So there is only one times it occurs. So you're going to give more amount of an importance for those kind of words. Okay. So at last, what they're trying to do, they're trying to multiply these two terms. So I will calculate the term frequency into inverse document frequency, and it will give you the TF-IDF score. Okay, let me work. We will work with some basic example. Like we will work with the example for this. So and we'll try to learn how this actually works. Okay, let us consider the corpus. This all together, I put it as a corpus. Okay, so we'll consider the 3 documents in the corpus. For a sake of a simpler example, let us consider there is only 3 records or 3 rows or 3 documents which exist in the corpus. So the first document says it is going to rain today, and the second document is going to say today I am not going outside, and the third document is going to say I am going to watch the season premiere. Okay, so these are the 3 documents which is going to be there. These are the 3 set of documents which is going to be in presence of a TF-IDF. Okay, now we are going to calculate the TF-IDF score or TF-IDF representation for each and every features. First step, you need to create a vocabulary. Okay, so if you want to create a vocabulary is nothing but it is a set of unique words, right? So I'm going to create a vocabulary. So if I need to create a vocabulary, not only the vocabulary, I need to count for the each and every words in the vocabulary. So that is relatively more important. Let me explain why it's relatively more important. So now in this case, I'm going to build a vocabulary. Vocabulary is a set of unique words. So you just build a vocabulary. So vocabulary is going to be going to, today, I am, it is rain. So we have 3 documents, right? So from the 3 documents, you extract all the unique words in the 3 documents. So you put it together over here. And next step is you calculate the count. So the count is the word going. Okay, so how many times the word going occurs in the corpus, or how many times the word going is occur all together. So if you see this, there is a going occurs one in the first one time, and there is going occurs in another time, and going occurs here another time. So it's going to be 1 plus 1 plus 1 is going to be 3. Okay, perfect. So my word going occurs 3 times in my corpus or 3 times in my all set of documents. Next 2. So where is 2? I have a 2 in my document one time, and I have a 2 in my document 2. No, I don't have a 2 in my document 2, so I don't increment my value of 2. So here, if you take the document 3, if you take the document 3, 1, 2, yeah, only 1, 2 occurs. So it's going to be 1 plus 1, 2. So in the all together in the corpus, the 2 occurs 2 times. So if you take today, today occurs like one time over here and another time over there. So you 1 plus 1, 2, because it doesn't have an occur in this space. Okay. So it's going to be 2. So like a similar fashion, if you're going to calculate for each and every unique word in your vocabulary or unique word in your corpus, you'll be getting the word count. So this is the first step in TF-IDF calculation. You just put a table. After putting a table, you list down all the set of unique words. After listing down all the set of your unique words, you just see how many times they appears in your corpus altogether. So and you put the count over here. So this is the first step, creation of your vocabulary. Okay, fine. So we are done with the first step and we're moving to the next step. Okay, next step in the process, I need to calculate the term frequency. Okay, let me revise the formula for the term frequency. What is term frequency? Term frequency is a number of occurrence of a word in the document divided by total number of terms in the document. Document in the sense records or rows in the corpus. So I'm going to calculate, okay, fine. I'm going to calculate the term frequency for the word it, okay? So for the document 1. So the term frequency is going to define as number of times the word it occurs in the document 1 divided by len of document 1. In this case, the len of document is like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So 6, and it occurs only one time. So it's going to be 1 by 6. So if you divide it by 1 by 6, it's going to be somewhere around 1.07 or 1, maybe round it off 1 divided by 6 is going to be 1.66667. It's going to keep on going. So you calculate for the document 1. So you will be calculating the term frequency for each and every document for the every words. So I calculate for going. Now coming back, you calculate for 2. If you calculate for 2, why am I telling? Because you have a set of your corpus, right? So you calculate for the word 2. So 2, how many times the 2 occurs in the document 1? Only 1 times. So 1 divided by 6, because 6 is the total number of words or the length of document 1, right? So it's going to be 0.16. Next one is a today. So you check for today. So today occurs only 1 time. 1 divided by 6, it's going to be 1 by 6, again 0.6. And you check your vocabulary. Next word is I. So you see how many number of times the I occurs in your document 1. I occurs 0, because I doesn't occur in the document 1, right? So 0 divided by anything is going to be 0. Simply we put 0. And next you see your vocabulary. Next word is an am. Now you see how many number of times the am occurs in the document 1. If you see how many number of times the am occurs in your document 1, it's going to be 0, because there is no am present in your document. So it's going to be 0 divided by 6. So never mind, it's going to be 0. Now you see the vocabulary. Next word is it, right? So you see how many number of times it occurs. So if you see here, the number of times it occurs is like 1 times. So it's going to be 1 by 6. It's going to be 0.16. So next one is, if you see for the is, it's going to occur only 1 time. So you put 1 by 6. So same for the rain. If you calculate rain is occur only 1 time in the document 1, you put 1 divided by length of document 1, so 1 by 6. So it's going to be 0.16. Okay, fine, fine. So we calculate the term frequency for the document 1. In a similar fashion, what I'm going to do, I'm going to calculate for the term frequency for the document 2 as well as document 3, because we have 3 different documents. It's if I have 5 5 different documents, I need to do the same process for the 5 different documents. Okay, perfect. Now for the document 2, same I'm going to repeat. So what I'm going to do today, I'm not going outside. Okay, you see the vocabulary, first word is going. Okay, so you see number of times the going is occur in the document 2. In this case, the number of times going occurs in a document 2 is only 1. So the numerator is going to be 1. And what is the denominator? Denominator is a number of terms or the number of words or the number of tokens present in a document 2, right? So in this case, it's going to be 1, 2, 3, 4, 5, 6. So same 6 words is present. So you just put divided by 6. So this is how you calculate for the document 2. So if you calculate for the document 2, this is going to be the answer. You're going to calculate for each and every word in the vocabulary for document 2. Perfect. So now we calculate for the document 3. So document 3, I'm going to calculate the term frequency for each and every word or a token in the document 3. How am I going to do? My first one is like I see my vocabulary list. So the first word is going. Okay. So fine. Going is there. I'm going to see how many number of times the going occur in the document 3. In this case, only one time the number of words going to occur in the document 3. So the numerator will become 1, and the denominator is going to be one number of terms or the len of doc 3. So in this case, len of document 3, in this case, it's going to be 1, 2, 3, 4, 5, 6, and 7 and 8. So it's going to be 8. So we are going to divide 1 by 8. So that is what the term frequency for the word going. So if you calculate 1 by 8, it's going to be 0.12. In the similar fashion, you calculate the word which is present in your vocabulary with respect to the document 3, and you calculate the term frequency for the document 3. Perfect. So my second step is over. What is my second step? My second step is I need to find the term frequency for each and every document by comparing to my vocabulary. Vocabulary is going to today I am, it is rain. So am I going to do? So like a numerator is going to be the number of terms the word is occur, T occurs, divided by the len of documents. So this is how I'll be finding my term frequency. Perfect. So now we moving on to the next step. What is the next step? Next step is I need to calculate inverse document frequency. Okay, fine. Let us revise the formula for the inverse document frequency. So the formula for the inverse document frequency is like the total number of documents. Okay, what is the total number of records divided by number of times the T which contain the term, right? So the number of documents which is going to contain the term T which we are trying to calculate for the IDF for. So in this case, if you, okay, let me explain why we are taking log in this place. Okay, perfect. Give me a couple of minutes. After explaining the IDF, I will explain why we are taking a log over this particular place, not rather than multiplying simply with your two product. So let us take in this case. So in this case, how many number of documents present in your corpus? That is going to be a numerator for calculating your inverse document frequency. In this case, it's going to be 3 because I'm going to have 3 documents, document 1, document 2, and document 3. I'm going to have a 3 documents. So the numerator is going to be 3, same for each and every documents because the number of documents are going to remain the same, right? So it's going to be 3. Now you see now you see the your this thing. Now you just see your vocabulary and you just calculate each and every value. Okay, perfect. So in this case, the first word is going. So going, coming back to going, so your numerator is going to be log times of 3. Why 3? The number of documents present in your corpus is 3. So 3 divided by how many number of times the word going occurs in all the documents in your corpus. First document contain going, yeah, it's right, 1. And second document contain going, yes, it's 1. And another document containing the word going, yeah, it's containing. So I'm going to make it as 3. Why 3? Because all the 3 documents I have the word going. So it's going to be log of 3 by 3. Perfect. So
excuse me, bro. Just one small doubt I have. Log to the base of what, bro?
log to the base of 2.
Okay. Thank you.
Yeah. Or else you can change the code in such a way that it's going to work for the log to the base of 10 also. So it's totally depends on the problem statement which you're trying to work. But basically, it's going to be log base 2. Okay, fine. So coming back, so 2, the word 2. Okay, so 2, how many times the number of words 2 occur in each and every document? So the document 1 contains 2, yes, it's contained. Document 2 contain 2, no, it's not containing. So the document 3 contain 2, yeah, it's contained. So it's going to be 2. So it's going to be 3 by 2. Perfect. So it's going to be 3 by 2. Now coming back to the next word in the vocabulary, that is today, right? So if you have a next word in your vocabulary today, you're going to check how many number of documents containing the word today or the term today. So the first document containing the term or the token today, yeah, it do. So you're going to increment the value 1, so it's going to be 1. And you see that the second document containing the word today, yeah, it contains word today, so it's going to be 2. The third document containing the word today, no, it's not containing the word document. It's not containing the word today in the document 3. I'm not going to increment the value, so it's going to be 2. So it's going to be 3 by 2. Perfect. the similar fashion, you calculate for all the words in your vocabulary. Let us calculate for the word rain. So if you calculate for the word is and rain, for example, if you calculate for is only occur one time, so it's going to be 3 by 1. It's going to be 3 by 1. And if you take a rain, so rain, if you calculate, it's going to be occur only one time. So that is in document 1. So it's going to be 3 by 1. So in this case, what we're trying to do, we are trying to give a importance to the word which is occur less frequent in the whole corpus. So rather than giving importance only to the frequent word, so we came some scenario where we'll be giving some importance to the word which occurs very less in your corpus. Okay, perfect. So now coming back to your question, why we are taking a log? Okay, so why I am supposed to take log? So what happened if I didn't take a log? Okay, let us say I'm working with the corpus. That particular corpus has a millions of unique words. My vocabulary length is million in million. Okay, it's relatively large. Let us say there is only one word occur. So the, for example, let us say only one word occur. So instead of saying that, let us say I have millions of records. Okay, in my data set I have millions of records. If in the millions of records, if I have only one word which is occurring in only one document, that is very unique word which is occurring in only one document, that is going to be million divided by one, which is relatively large. If you multiply any term with a million kind of things, so your TF-IDF will be extremely large, right? So in order to avoid the booming effect, or in order to avoid the extreme large values, we are taking a log, because log is going to dampen the effect. So that is why we are considering taking a log in order to prevent the value overshoot, because there is we don't want the value to be exceed more than some range, because that is not good for any machine learning model to work on. Because if you supply huge amount of value to the machine learning model, it tends to bias the word, right? So that is why we take a log. You can imagine is a kind of a normalization kind of things, or it's like a damping effect. So where you try to reduce the value, because log is always try to reduce the value, right? So that is what we are trying to do in case of an inverse document frequency. We are taking a log. Okay, perfectly fine. I already calculate the TF values and I already calculate the log values. Now I'm going to see. So this is the TF-IDF values which we calculate. This is the term frequency values which we already calculate. Perfect. So now if you see IDF, right? So if you see your IDF, so IDF is what we calculated right now. You can take your log values, and this is a total representation. This is your IDF values, and this is your term frequency values. Perfect. Now what I'm going to do? Now I'm going to multiply TF into IDF, right? So I'm going to multiply term frequency into inverse document frequency. So for the going word, I'm going to multiply all these terms together. So for example, in document 1, let us take the document 1, okay? So for this document 1, I'm going to multiply with respect to my IDF, because this is a term frequency. I multiply with the IDF value. So my document 1 is going to be 0, 0.07, 0.07, 0, 0, 1, 0.17. This is nothing but, sorry, this is nothing but you just multiply this particular value with respect to your IDF value over here. So that is what we are trying to do. And for the each and every word, right? So going to today I am, and it is going to rain. So 0.6 into 0 is what we are going to get for going in 0. So it's going to be 0. And 0.16 into 0.41, you get to some value. So this is how you just multiply for the each and every words that correspond to each and every document. So this is what your feature representation. Okay, fine. Now coming back to the previous methods, if you see the previous method, that is going to give you some kind of values, which is either going to calculate your frequency or either going to represent with a binary representation. It never cares about something giving some weights, right? So in this case, if you see I'm giving some weights or a kind of ways in which you can see there's some kind of good representation or good partial representation. So let us see, there's something 0.17, 0.17. I don't give any extreme values, or I didn't get any minimal value. I just give some weights to the words which is occurring really important. For example, in the word 1, you see there is something giving importance to rain, right? So that is what we're trying to do. For example, if you take the document 2 and 3, so today I'm not going to outside, I'm not going to watch the season premiere. So I get something good representation as compared to the previous methods, because the previous method only carries about the words in the words in the document. It doesn't compare with respect to the whole corpus, right? So in this case, we just somehow try to map the between the term frequency as well as the document frequency. Document frequency, we give importance to the less occurring words, because sometimes that may be the like a factor in our problem kind of things. So TF-IDF is a better representation. Right now, I'm saying some of the industry use cases were still using your TF-IDF. So there are some cases where TF-IDF is used till now. So TF-IDF is a good way to start when you're working for the feature representation. Okay. There's something to tell you on. So in sklearn, right? So we are mostly dealing with your sklearn packages. So in the sklearn packages, they use slightly a different formula. So they add the constant term I to your inverse document frequency, because they don't want the zero division error. So in order to prevent the zero division error, they just add one single constant 1 to the ID inverse document frequency. So if you're trying to do it in a coding method, so you'll be getting a slightly a different answer for your inverse document frequency. So that is why some people give the warning to use properly, because there's something called parameter smooth IDF you make as true, because there is a default value that's going to have the constant one. So that particular thing is going to prevent you from a zero division error. Perfectly fine. We are going to get a slightly different value for your IDF factors, right? So what are the advantages which we are going to get in case of term frequency inverse document frequency? So the advantages, if you ask me the advantages, so advantages in the sense it's going to penalize the high frequency words and low frequency words in the corpus. Like it's going to give the good representation with the balance factor of the both the terms, right? So because we calculate the TF and we calculate the IDF and we just multiply it with together and we just make a somewhat balance, right? So another disadvantage is still we cannot able to capture the positional information. So if you just swap the words, because if you see, um, it's not it is not it is going to rain today. If I swap the word and I calculate TF-IDF, it's going to be remain the same, right? So it doesn't capture any semantic, or like it doesn't capture any positional information. So another disadvantage is like TF-DF is highly corpus dependent. Yeah, exactly. So whatever the data set I'm going to train on, my TF-IDF is going to remain the same. It doesn't allows me a generalization. So for example, there is something word which came out of new, which is relatively new to the vocabulary. My model is going to be struggle. My TF-ID is going to be struggle. It couldn't handle generalization. So it's highly data dependent and or highly corpus dependent, we can say. So these are some disadvantages. So this disadvantages which we can try to solve using something called word embedding techniques. So that we'll try to see in the next class. Today we'll go into the coding session. So before going into the coding session, let me give you some basic overview of what is word embedding. Okay. So word embedding in the sense like I'm going to represent my feature as a vector. Right now we are doing a vector. Vector is a continuous form of a number, right? So that word embedding is going to give a similar representation for the words or the for the text, which is going to represent a similar thing. For example, let us say I love teaching NLP. Okay, and there is another text which is going to say I love teaching coding. Okay, so there is third document which is going to say I hate teaching. I hate hate teaching. Okay, now if I going to create a representation for these three words in the space, so the first two words, right, the first two text or the first two documents is going to be more similar together. It's going to sit in a more similar together rather than like the last one, I hate teaching, because that is completely different, right? So we are going to see how to create those kind of embeddings technique, how to create those kind of vector embeddings for the different words. If we see this example, the mathematics and statistics are similar together, but the tigers and lions are similar together, but tiger and mathematics is not similar together, right? And vice versa. So this is how the feature representation is going to look like. So we are going to implement the methods which is responsible for generating these kind of embedding techniques. So this is the like a state of art. There is something called SOTA. SOTA is nothing but a state of art technique. So there is some SOTA technique for your word embeddings. So in this next class, you'll be exposed to something called word to vec. Okay, it's a kind of ANN technique, like artificial neural network. With the help of ANN, you're trying to build the embeddings for the model, right? So we'll see how to build a word to vec model, and we'll see, and we will encourage, like we will appreciate how the word to vec work as compared to the different methods. So tomorrow we'll see on the word to vec part, as well as the model building, logistic regression, as well as naive base. So but today's session, coming back, we see these different methods, right? So we try to implement in code. Okay. Okay, so if you want all of the guys to work with me like hands-on session, you just log into their Google Colab and work it with me. Like we'll work on some basic example for all the representation techniques. So I will give you time. So you just log into the Colab or a Jupyter or any compiler kind of things. Okay, so we will start with the importing the packages. So some of the basic packages, like I will import something NumPy. So for numerical Python. Okay, perfect. So we'll start with TF-IDF because lastly we saw, right? So if anything wants, we'll come and import over here. So yeah, we'll start with something called TF-IDF, right? So okay. So for TF-IDF, I will be importing something called from sklearn. So from sklearn dot feature extraction. Sklearn dot feature extraction. We are working on text, so you put text. If you're working on image kind of things, you put image. So right now we are working on text. So from sklearn dot feature extraction dot text, you just import TF-IDF vectorizer. TF-IDF vectorizer. Yeah, cool. So you just import TF-IDF vectorizer. Okay, fine. So we take the same example. So document one. One second, let me see. It is going to rain today. Today I'm not going outside. I'm going to watch season premiere. Okay, fine, perfect. So I just write document one as it is going to rain today. Document two is going to be today I am not going outside. I am going to watch season premiere. And your document three going to contain. Oh shit, I can do this. Perfect. So this is what the document three documents. Okay, perfect. So we're going to create a corpus. So let me name corpus as COU. Corpus is going to contain all your documents, right? Document one, document two, and your document three. So if you see a corpus, it's going to be consists of all the three set of documents. Perfect. Now we are going to use a TF-IDF. If you don't want to calculate everything from the beginning, so we have a helper function. So I'm importing one function. So that is called as, I'm calling the method. Okay, first I need to give a name, right? So let us say TF-IDF, which is nothing but TF-IDF vectorizer. Yeah, perfect. I'll call this object TF-IDF vectorizer. So there is something function called fit transform. So fit transform is going to apply whatever you're trying to do, right? So you just put fit underscore transform. So fit underscore transform, you need to give your corpus, not the documents. So I just give that corpus, okay? Perfect. So that's all. Like if you want to explore, let me give you one thing. So your TF-IDF thing is right done. So there is something called, I already told you, right? There is something called DAR. So if you don't any methods, don't know what are the methods present in something, you use a DAR. So you give an object. So I'm giving the object as like TF underscore IDF. I need to get all the methods which is present in the object. So there are like a huge lot of methods. So we'll see not just like vocabulary kind of things. So we use vocabulary. So vocabulary. And we'll see what is our vocabulary for this document or what the corpus. Yeah, perfect. So you see like it occurs, it is going to rain today. So these are the vocabulary. So vocabulary is nothing but this is a word, and this is the index, not the count. It's an index. So at what index in particular words is occur? So this is the index, not the word, right? Not the count. It's an index. Okay, fine. So I need to get like a features. Okay, what is features? Like what are the unique words? You also have another thing called features. Get features name out. So that particular thing is going to give you a features name. Like what are the features which I represent? So in this case, let us explain what is a feature. So we have these terms, right? The unique words in the above. So you can also get what are the terms which are present in the above by using the same function like get underscore feature. I think get underscore feature names out. Yeah, this function is going to give you an array. Yeah, so this particular array is going to represent what is their feature representation, like how is going to arrange together. So in this case you can see I'm going, it is in this way is going to arrange. So you just see how it arrange now. Okay, fine. Now I need to get let us say I need to get what is an idf value. So I'm interested in getting know what is my idf value. So it's perfect, we already done, right? So if you just see this line, we already fit transform. If you just put x dot to array, you get your representation. We are already done with the representation, but we are now exploring outcomes. So this is a representation for the corpus. So if you see the first document 0, so this is the feature representation. So this is a feature representation for the first document, that is document 1, or you just say corp 0. So it is going to rain today can be represented in this form. So we are already done with that, but now we are exploring some features with respect to TF-IDF. If you see, like I need to get the IDF values for each and every word in the vocabulary, you have something called TF underscore IDF, your object, and you just put dot and you call the method called idf underscore. So if you put idf underscore, you'll get an array. That array is calculated consists of all your idf values. Okay, fine. So what is this idf value? Okay, fine. Let us say there is some vocabulary, right? This vocabulary will have an index number. So for example, I need to calculate the idf for the word am. So the index of the am is 0, right? So if I put tf underscore for idf underscore and I put 0, this is going to give my idf value for the word am. It's just nothing but 1.267. So 1.2867. So if you calculate for the word, let us say today, so the index of the word today is 11, right? So if you put 11, so you will be getting an IDF value for the word today. And if you want to get the IDF value for the word premier, so you just put 6 because its index is 6. So you put 6 and you'll be getting the word like IDF value for your premier. Okay, perfect, fine. So this is how you'll be getting the values. So as I said already, like sklearn is going to use a different formula to calculate your IDF, but doesn't make any sense. So you can use your own formula or you can code from the beginning. So you can use the same sklearn formula also. Let me explain you. Like we print out all the IDF value. Okay, so you just say for feature in feature like for feature in this thing. Uh, I'm going to print out the values, okay, for each and every feature and corresponding IDF value. So you just put index to you have vocabulary, right? What is your vocabulary? This is your vocabulary. You can store this vocabulary, no problem. You can store to sometimes like vocab. There is a dictionary, so dictionary, so you don't you can easily access. So and you just give the key. So key is going to be a feature because each and everybody you are going to calculate, right? So that is going to be a feature. Sorry. So from you just use a print statement. So you just format and you put your feature. There is going to be here and corresponding IDF value, right? Going to be EF underscore IDF dot IDF underscore here INDX. Perfect. If you just run this, you will be getting the each and every feature and corresponding IDF values. Perfect. So we are done with the TF IDF representation. Now we will move into the something like yeah, okay, fine. We'll see bag of words. We'll see bag of words and how it works. Okay, perfect. So what example we saw for the bag of words? Yeah, the same example which we see for this. So for the bag of words, you need to import something called count vectorizer. So for TF-IDF, you import TF-IDF vectorizer. For bag of words, you import count vectorizer. It's the same thing. You just say from sklearn dot feature underscore extraction. You just import count vectorizer. Cannot import count vectorizer. What happened? Oh shit. Okay, fine. Dot text. We import count vectorizer, right? So now we are good to go. So you just you need to create a corpus, right? So for creating a corpus, say document one is going to be the cat in the hat. That is document one. Yeah, the cat in the hat, the dog in the house, the bird in the sky. The document two is going to be the dog in the house. And your document three is going to be the bird in the sky. The bird in the sky. Yeah, perfect. You just create a corpus. Corpus is a combination of all your document one, document two, document three. Perfect. If you print your corpus, sorry, my bad. print your corpus, you'll be getting perfect. So now you just call your count vectorizer, you call it with your BOW as your count vectorizer. Perfect. So as I said already, if you don't know any methods in the for the object, you just put the dir of above. So you'll see all the methods respected to the bag of words or the count vectorizer, sorry, count vectorizer. So we are going to use something called fit underscore transform to create a feature representation. You just put x. So x is nothing but your BOW dot underscore transform, and you put your corpus. So now if you put x dot to array, you get your representation. So this is a representation. How this representation appears, in order to get this one, you just put your bow dot get underscore feature underscore names underscore out. If you call this method, so yeah, perfect. Bird, cat, dog, hat, house, in the sky. In sky the okay. So for the first word, what is our first word? There is document one, or we say corpus of 0. And let me take the first text representation. Okay, perfect. So the first word says the cat in the hat, right? So the cat in the hat, if you see the first word is correspond to bird. So there is a bird appears in this? No, right? So you put 0. And second one is your cat. The cat appears in the text, right? Yeah, one time. So you put 1. Next one is your dog. So dog appears in the text? No, you put 0. And you put hat. Hat appears in the text? Yes, it appears only 1. So you put 1. Next, house. House appears in the text? No, it doesn't appear, so you put 0. And in appears only 1, so you put 1. And sky. Sky appears in the text? No, so you put 0. And there is a word the. The appears 2 times, right? You put 2. So this is how the feature representation are constructed for this. If you want to know, you just put features name out. So if you put get features name out, so you'll just have an idea on how the representation arranges. So perfect. Now you just see for the second or first document, like a second document, it's like this. You can put 1, and you can see how this old terms appears. Perfect. Now you all know how the terms appears, like you know how these terms appear, right? So now coming back to some things what we can do, we can get features name. We have df preprocess set params. Okay, perfect. And also if you want to see your vocabulary, same thing what you're going to do, bow dot vocab. And after putting bow dot vocab, we are getting 2 names, so you just print it out. So this is a vocabulary. So this is the unique words and the corresponding index values. So this is what the vocabulary. You can imagine this on this as a sorted value. Sorted of the key values of this will be the feature names. Perfect. So we are left with like n-gram, no? Okay, let me explain how n-grams works, like an important one. Because there is some NLP domain, some specific with respect to n-gram analysis. If you have time in the end, we'll do n-gram analysis kind of things, and we'll try to benchmark something. So you take the text. Okay, let us say for the sake of simplicity, I'm taking only one text. So the text is going to be I love. So we'll use the same text. Love in the house. So we'll see. So we don't want to import anything with respect to n-gram because it's come from bow-gram, right? You can use a count vectorizer itself. So you just put n-gram equal to count vectorizer. So in the count vectorizer, now you need to add some parameters. You need to give some parameters. So the parameter is nothing but you need to give your n-gram range. Okay. So n-gram range. Perfect. So let us say I'm doing for an unigram. So if I want to do for an unigram, you need to give 1, 1. One is the starting value, and one, like the first value in the tuple is going to be your start value, and second value is going to be a max value or stop value. In this case, for a unigram, let us put 1, 1. So and you just say x equal to n-gram. Same thing, fit underscore transform for your text. Uh, Perfect. Now if you see n-gram dot get feature feature names out. You see, it will be a single word kind of thing. Dog, house in the, okay, perfect. So if you want to get the representation, you just put x dot to array, and you see this is a representation. Okay, fine. So let us say I need to do for a bigram. So bigram is like 2 comma 2. So for the bigram. So same bigram you just put, and you see you would have two words like together, do in dog in, sorry, in the dog, the house. And if you see the representation is going to be 1 1 1 1. Perfect. So let us say I need to get a trigram. So if you need to get a trigram, you put 3 comma 3. You have a three words, right? So dog in the house, the dog in. Okay, perfect. Okay, for example, let us say I need a unigram as well as bigram. So you can give 1 comma 2. One is like a unigram and two is a bigram. So you can give 1 comma 2, and you can see how it can. You see there are some words dog in, house, the, or the unigrams, and the bigrams are the dog in the, and the dog, the house. So those are the bigrams. Let us say I need to have a unigram, bigram as well as trigram. So you just train your maximum value of your df, that is a range. So 1 comma 3. So this particular thing is going to give you a unigram, bigram as well as trigram together. Okay, fine. So you can ask me what happen if I want to keep only the bigram as well as trigram. You just give 2 comma 3. So bigram and trigram you can get. So this is for the n-gram kind of thing. So I think we are good to go. So this is for the n-gram. So tomorrow's sessions, so what we're trying to do is we'll start with the word embedding techniques. So word embedding technique, we'll try to explore word to vec as well as your word to vec two different techniques. So from the word to vec techniques, after seeing the word to vec techniques, before going into the word to vec, I know some of them from the second years as well as some of them from the third years IoT. I know you people not very much aware of an ANN kind of things. So I'll spend some more time in teaching you an ANN. What is an ANN? Basic one, like to get understanding of your glove kind of mechanism. I will teach you the basic form of an ANN. So then we'll see the word embeddings. So after seeing the word embeddings, we'll move into the logistic regression and naive base. We see how the logistic regression algorithm and naive base works, and we'll start like coding for the word embedding methods. And we'll, with the help of all those kind of methods, we'll try to build a machine learning model for the spam classification. So that is an agenda for the tomorrow's class.